Imagine, if you will, a lone spacecraft, its engines silent, drifting through the inky blackness between planets. It is not accelerating, nor is it slowing down. It simply is, moving at an unchanging speed, on a path that seems to stretch into eternity. How is this possible? On Earth, if you push a ball, it rolls a short distance and then stops, brought to a halt by the subtle drag of air and the friction of the ground beneath it. If you throw a stone, it arcs through the sky before gravity pulls it down and air resistance gradually diminishes its forward momentum. Yet, in the cosmic theater, planets have been circling their stars for billions of years. Galaxies are spinning with majestic grace, and asteroids hurtle across unimaginable distances, all without any visible force continuously propelling them. This fundamental difference, this perplexing absence of a cosmic break, lies at the very heart of how celestial bodies move for millions upon millions of years without ever seeming to tire or cease their journey. The answer, in its most elegant simplicity, resides in a concept so profound it underpins all motion in the universe: inertia. Sir Isaac Newton, centuries ago, articulated this principle with remarkable clarity in his first law of motion, sometimes called the law of inertia. It states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction, unless acted upon by an unbalanced external force. On our bustling planet, where almost every movement is immediately met with resistance, this law might seem counterintuitive. We are so accustomed to seeing things stop, to observing objects requiring continuous effort to maintain their speed, that the idea of perpetual motion feels almost fantastical, like something out of a science fiction novel. But remove the omnipresent forces of friction and drag that define our terrestrial experience, and Newton's law reveals its universal truth with breathtaking clarity. In the vast, silent expanse of space, friction is, for all intents and purposes, entirely absent. Here, there are no rough surfaces to impede an object's slide, no gritty grains to create resistance between moving parts. If you were to give a push to an object in the vacuum of deep space, that object would continue to glide away from you at precisely the speed you imparted to it, maintaining that velocity indefinitely. There is nothing to slow it down. This absence of mechanical friction is a cornerstone of why celestial bodies maintain their motion. Imagine two colossal tectonic plates on Earth grinding past each other, generating immense heat and colossal earthquakes. That immense friction is a powerful dissipative force, constantly trying to bring things to a halt. In space, such interactions are rare and, when they do occur, often involve collisions that dramatically alter motion rather than gradually reducing it. But the gentle, everyday friction we experience from rubbing our hands together to a car braking simply does not exist in the cosmic void. Even more significant than mechanical friction is the pervasive drag caused by atmosphere. On Earth, every aircraft, every bullet, every falling raindrop is constantly battling against the invisible yet very real resistance of the air. This atmospheric drag is a powerful force, converting kinetic energy into heat and slowing down anything that moves through it. Even the most streamlined shapes are subject to its relentless grip. But in the vacuum of space, save for the infinitesimally thin wisps of gas and dust that populate interstellar and intergalactic regions, there is no air, no medium to push against. A planet hurtling through its orbit encounters no atmospheric resistance, no dense cushion of gas to sap its momentum. This means that once a celestial body has acquired a certain velocity, there is nothing in its path to gradually erode that speed. It is free to continue its journey, unhindered and undisturbed, for literally billions of years. This allows for an extraordinary economy of motion, where no energy needs to be continuously expended to keep things moving. This perfect cosmic ballet, sustained by inertia, allows for the truly staggering longevity of celestial movements. Consider the Earth itself, which has been orbiting the Sun for approximately 4.5 billion years. It travels at an average speed of about 30 kilometers per second, covering an enormous distance every single day. Yet, it does so without any rocket engines firing, without any visible push from an external source. Its motion is a testament to the initial impetus it received during the formation of the solar system, combined with the continuous, guiding hand of gravity. The same principle applies to our Moon, which has been circling Earth for an equally immense span of time, or to Jupiter, a colossal giant that has been majestically making its way around the Sun for epochs, its famous great red spot swirling for centuries. These are not instances of magical self-propelling machines. They are simply objects adhering to the fundamental laws of physics in an environment where resistance is negligible. Even the minuscule traces of matter that do exist in space, such as the faint solar wind, micrometeoroids, or stray hydrogen atoms, exert only the most infinitesimally small amounts of drag over vast spans of time. While scientific instruments are sensitive enough to detect these minute interactions, their cumulative effect on massive celestial bodies over typical timescales of observation is effectively zero. For all practical purposes, a planet or a star is moving through an empty void. This profound emptiness is precisely what enables the seemingly miraculous, tireless movement of everything from comets on their vast, elliptical journeys into the outer reaches of the solar system, returning perhaps only once every thousands of years to distant galaxies whose constituent stars are rotating at tremendous speeds for eons. The fact that the universe is predominantly composed of vacuum is not just a spatial characteristic, it is a fundamental enabler of cosmic motion itself. This understanding of inertia also helps us appreciate that objects in space do not use up energy to maintain their motion. On Earth, we are constantly fueling cars, recharging batteries, or eating food to provide the energy needed to overcome friction and gravity. But in space, an object's kinetic energy, the energy of its motion, is conserved because there are no significant forces doing work to transform that energy into other forms, such as heat or sound. Once an asteroid, for example, is sent hurtling on its trajectory, it simply keeps that energy of motion. It is not being powered in the way a machine is. It is simply adhering to its fundamental state of motion. This is a subtle but crucial distinction. Celestial bodies are not actively working to move. They are passively continuing a state of being that began billions of years ago. Their motion is inherent to their existence in the frictionless void. The vast scale of the universe further accentuates this phenomenon. The distances between stars, between galaxies, are so immense that even objects traveling at extraordinary speeds take millions or billions of years to traverse them. If there were even a tiny amount of resistance spread out over these unimaginable distances, motion would eventually cease. But because the vacuum is so perfect, and the space is so immense, the cumulative effect of any minuscule drag becomes negligible. It's a bit like a single dust mote on a vast, polished ballroom floor. Even if there were a faint breeze, its effect on a cannonball rolling across that floor would be imperceptible over short distances and over cosmic distances. That imperceptibility allows for eternal travel. The universe is a stage set for perpetual motion, an environment where the laws of physics can play out without the constant interruptions we experience in our everyday lives. So, when we gaze upon a star, steady in its position in the night sky, we are not seeing something stationary. We are witnessing an object in profound motion, likely rotating on its axis, and perhaps orbiting the center of its galaxy at speeds that defy comprehension, all while adhering to the silent, unwavering command of inertia. It is an unseen force, or rather, the absence of opposing forces, that allows this magnificent, tireless dance to continue for cosmic timescales. The cosmos does not require fuel to keep its inhabitants moving. It simply requires the vast, near-perfect vacuum of space to allow the initial impetus to persist, defining the very essence of how everything, from the smallest asteroid to the grandest galaxy, moves with an unwavering, eternal grace. The deep memory of the universe is etched not just in the ancient light that reaches us, but in the enduring, perpetual motion of everything within it. While inertia explains why things keep moving in space, it doesn't fully account for how celestial bodies navigate their intricate curved paths rather than simply flying off in straight lines. Imagine our solitary spacecraft, still drifting, but now it approaches a massive star. If inertia were the only force at play, the spacecraft would maintain its straight trajectory, eventually sailing past the star and into the infinite void. Yet, we know that planets, moons, and asteroids are not launched into space in perfectly straight lines. Instead, they are locked into graceful, continuous orbits around more massive objects. This intricate, ceaseless celestial ballet, a dance that has unfolded for billions of years without missing a single beat, is entirely orchestrated by another fundamental force: gravity. Gravity is the invisible choreographer, the master puppeteer that continuously bends the paths of celestial bodies, ensuring their eternal cyclical motion. Gravity, as articulated by Newton, is a universal force of attraction between any two objects that possess mass. The greater the mass of the objects, and the closer they are to each other, the stronger the gravitational pull between them. It is this omnipresent, yet often imperceptible force that governs the grand architecture of the cosmos, from the smallest asteroid circling a planet to the colossal galaxies pulling on each other across intergalactic space. Think of the Earth orbiting the Sun. If the Earth were simply pushed into space with a certain velocity and no other force acted upon it, it would indeed travel in a straight line as dictated by inertia. However, the immense mass of the Sun exerts a powerful gravitational tug on Earth, constantly pulling it inwards. This inward pull continuously deflects the Earth from its otherwise straight path, bending its trajectory into the elliptical orbit we observe. It's a delicate balance, a perpetual struggle between two fundamental principles. The Earth's inertia compels it to continue moving in a straight line, to escape the Sun's embrace and hurtle into the darkness. But the Sun's gravity relentlessly pulls it back, curving its path. The Earth is, in essence, constantly falling towards the Sun, but because it also possesses a tremendous sideways velocity, it continuously misses. This endless state of falling and missing is the essence of an orbit, It is not that gravity stops the Earth from moving in a straight line. Rather, it redirects its straight-line motion into a continuous curve. The speed of the Earth and the strength of the Sun's gravity are perfectly matched, creating a stable, long-lasting orbit that has persisted for billions of years. If the Earth moved faster, it would escape the Sun's gravity and fly off into space. If it moved slower, the Sun's gravity would eventually pull it inwards, causing it to spiral and ultimately collide. The harmony of their interaction is a testament to the precise balance established during the solar system's formation. This gravitational embrace extends far beyond individual planets and stars. Consider our own Milky Way galaxy, a majestic spiral of hundreds of billions of stars. Each of these stars, including our Sun, is orbiting the supermassive black hole at the galactic center. The combined gravitational pull of all the stars, gas, and dark matter within the galaxy creates a gravitational field that shapes the paths of individual stars, guiding them through vast circular trajectories. The Sun, for instance, completes one orbit around the galactic center approximately every 230 million years, a cosmic year. This colossal journey is also a perpetual fall, a never-ending redirection of inertial motion by the collective gravity of the galaxy. Just as Earth falls around the Sun falls around the galactic center, a multi-layered dance orchestrated by the same universal force. The Moon's orbit around Earth is another classic example of gravity at work. While the Moon exerts its own gravitational pull on Earth, causing the tides, it is Earth's much larger mass that dominates the interaction, keeping the Moon locked in its familiar elliptical path. The Moon, too, is constantly trying to fly off into space due to its inertia, but Earth's gravity tirelessly tugs it back, maintaining its orbital dance. This dynamic equilibrium is robust and incredibly stable over astronomical timescales. Slight perturbations from other planets can influence these orbits over millions of years, causing them to subtly change shape or orientation. But the fundamental gravitational bond remains unbroken. Indeed, the very formation of celestial bodies is deeply intertwined with gravity. During the birth of a star system, vast clouds of gas and dust begin to collapse under their own gravity. As this material falls inward, it starts to spin faster, a concept we will explore in the next section, and the central mass grows. The remaining material flattens into a disk, and within this disk, smaller clumps of matter begin to coalesce, again under the influence of their mutual gravity. These growing clumps, the protoplanets, sweep up more and more material, their gravitational pull becoming stronger, further solidifying their existence. The initial momentum imparted during this chaotic formation, combined with the continuous gravitational interactions, sets the stage for the enduring orbital motions we observe today. Gravity also shapes the grand cosmic structures we see, from clusters of galaxies to superclusters. Galaxies themselves are not isolated islands in space. They are often found in groups or clusters, bound together by their mutual gravitational attraction. Our Milky Way, along with Andromeda and other smaller galaxies, is part of the local group, all slowly moving towards a common gravitational center. On even larger scales, galaxy clusters are drawn together into immense filaments and walls, creating the cosmic web, the largest known structures in the universe. This large-scale organization is a direct consequence of gravity, acting over billions of years, slowly pulling matter together and shaping the fabric of the cosmos. It is important to remember that gravity, unlike friction, does not dissipate energy in the way a brake does. When an object falls towards another due to gravity, its potential energy, energy of position, is converted into kinetic energy, energy of motion. In a perfect two-body system in a vacuum, without any other influences, this exchange of energy is reversible and cyclical. The object speeds up as it approaches the more massive body, converting potential energy into kinetic energy, and then slows down as it moves away, converting kinetic energy back into potential energy. The total mechanical energy, kinetic plus potential, remains constant. This conservation of energy is another crucial reason why orbits can persist indefinitely. There is no fundamental energy loss mechanism inherent in the gravitational interaction itself that would cause the orbiting body to eventually stop or fall inwards, assuming no other forces are at play. Over truly immense timescales, other subtle gravitational effects do come into play. For instance, tidal forces caused by the differential gravitational pull of one body on different parts of another can lead to very slow changes in orbits. The Moon is slowly, almost imperceptibly, moving farther away from Earth each year due to tidal interactions. Similarly, the Earth's rotation is gradually slowing down. These are not instances of gravity stopping motion, but rather gravity transferring angular momentum within a system, leading to subtle adjustments over billions of years. These are not dissipative forces in the same sense as friction or air resistance. They are part of the ongoing, dynamic gravitational dance that subtly reshapes the cosmic landscape. The beauty of gravity lies in its continuous, unwavering presence. It doesn't act intermittently, pushing once and then receding. It is always there, always pulling, always influencing, constantly bending the straight lines of inertia into the elegant curves of orbits. This constant redirection is what creates the appearance of perpetual circular or elliptical motion. If gravity were to suddenly vanish, the planets would indeed fly off into space in straight lines, maintaining their current velocity. But because gravity is an intrinsic property of mass, a fundamental force woven into the fabric of the universe, it remains the eternal sculptor of cosmic paths, ensuring that celestial bodies continue their graceful, age-old journeys around their gravitational anchors. From the swirling dust grains in a nascent solar system to the majestic spiral arms of a distant galaxy, gravity is the invisible hand that keeps everything in its place, or rather, keeps everything in its particular, curved motion. It is the force that binds, that coalesces, that organizes the chaos of the early universe into the structured, predictable systems we observe today. Its enduring power ensures that the celestial clockwork, once set in motion, ticks on for eons, performing a timeless ballet where every participant is both pulled and propelled, forever caught in the gravitational embrace of its cosmic partners. This continuous dance, sustained by the constant redirection of inertia, is what allows us to gaze upon a night sky filled with seemingly eternal moving lights, each one a testament to the profound and patient work of gravity. Beyond the grand spectacle of celestial bodies tracing vast orbits around each other, there is another fundamental form of sustained motion that has captivated thinkers for centuries: rotation. Planets spin on their axes, stars whirl, and entire galaxies rotate with majestic, breathtaking speed. These rotational movements, too, endure for billions of years without any obvious engine driving them. What invisible force ensures that Jupiter continues its rapid 9-hour rotation, or that our own Earth keeps spinning, giving us day and night without ever slowing to a halt? The answer lies in another profound principle of physics, the conservation of angular momentum. This cosmic law dictates that a rotating object will continue to rotate at the same rate and in the same orientation unless an external torque acts upon it. Imagine, if you will, an ice skater performing a spin. When she extends her arms, she rotates relatively slowly. But as she pulls her arms inward, close to her body, her spin dramatically speeds up. She hasn't pushed off with any additional force. She has simply redistributed her mass. This remarkable phenomenon is a perfect demonstration of the conservation of angular momentum. Angular momentum is a measure of an object's tendency to continue rotating, and it depends on two key factors: its mass and how that mass is distributed relative to its axis of rotation, its moment of inertia, and its angular velocity, how fast it is spinning. The law of conservation of angular momentum states that if no external torque, a twisting force, acts on a system, its total angular momentum remains constant. In the vast, almost frictionless environment of space, external torques acting on isolated celestial bodies are incredibly rare or utterly minuscule. This means that once a planet, star, or galaxy acquires a certain amount of angular momentum during its formation, it retains that momentum almost indefinitely. There's no atmospheric friction to slow down its spin, no solid ground to create drag. Just like an object moving in a straight line due to inertia, a rotating object in space keeps on spinning, a silent testament to the laws of the universe. Let's delve into the birth of a star or a planet to understand how this initial spin is imparted. It all begins with a colossal, diffuse cloud of gas and dust in interstellar space. These clouds are incredibly vast and sparsely populated, but they contain immense amounts of mass. Due to gravitational instabilities, or perhaps a nearby supernova shockwave, parts of this cloud begin to collapse under their own gravity. As the cloud contracts, all its constituent particles move closer to the center. Here's where angular momentum becomes critical. Even if the original cloud had only a minuscule, almost imperceptible overall rotation, as it shrinks, that rotational motion is amplified. Think back to the ice skater. When the mass of the cloud is spread out, its moment of inertia is very large. As it collapses, its mass becomes concentrated towards the center, drastically reducing its moment of inertia. To conserve the total angular momentum, the cloud must, therefore, spin faster. This is why nearly all celestial bodies, from the smallest asteroids to the largest galaxies, exhibit rotation. The primordial, barely noticeable swirl of a collapsing gas cloud is transformed into the rapid, majestic spin of a star or planet. Our Sun, for example, rotates once every approximately 25 Earth days at its equator, a legacy of the spinning nebula from which it formed. Planets, too, inherit this rotational momentum. As a protoplanetary disk forms around a young star, material within that disk is also rotating. As clumps of matter within the disk coalesce to form planets, they pick up this rotational energy, leading to their own axial spins. The Earth, for instance, completes a rotation once every 24 hours. This spin is a direct consequence of the angular momentum it acquired during its formation from the swirling protoplanetary material. Over billions of years, this spin has largely remained consistent, powering the cycle of day and night without requiring any continuous external energy input, while the conservation of angular momentum dictates that spin should be eternal, there are subtle forces that can cause changes over truly vast timescales. Tidal forces, for instance, play a significant role. The Moon's gravitational pull on Earth creates a slight bulge in Earth's oceans and crust. Because Earth rotates faster than the Moon orbits, this bulge is pulled ahead of the Moon. The Moon, in turn, gravitationally tugs back on this bulge, creating a tiny braking effect on Earth's rotation. This is why Earth's rotation is very gradually slowing down, leading to imperceptibly longer days over millions of years. Simultaneously, and in accordance with the conservation of angular momentum for the Earth-Moon system, the Moon is slowly spiraling farther away from Earth. These are not instances of angular momentum being destroyed, but rather transferred within the system. The total angular momentum of the Earth-Moon system remains constant, but it is redistributed. Similarly, other planets in the solar system, particularly the gas giants, experience complex internal dynamics that can affect their rotation. Powerful atmospheric currents and internal convection can cause slight, long-term variations in their rotational periods. However, for the most part, these effects are minor compared to the immense angular momentum locked within these colossal bodies. The vastness of their mass and the near absence of external frictional forces mean that their spins remain remarkably stable over billions of years. The rotation of galaxies presents an even grander scale of angular momentum conservation. Spiral galaxies like our Milky Way are immense rotating disks of stars, gas, and dust. The entire disk spins, with stars closer to the center completing orbits much faster than those on the outer edges. This differential rotation is a complex dance governed by the distribution of mass and the gravitational field of the entire galaxy. The colossal angular momentum of a galaxy is a legacy of the initial angular momentum of the enormous primordial gas cloud from which it formed. As that cloud collapsed, it flattened into a disk and spun up, just like a single star or planet. The sheer scale and mass involved mean that galactic rotations are among the most stable and long-lasting forms of motion in the universe, continuing for tens of billions of years. Even black holes, the ultimate gravitational behemoths, conserve angular momentum. Many black holes are observed to be rapidly spinning, a characteristic inherited from the massive stars that collapse to form them. The conservation of angular momentum ensures that as a star collapses into an incredibly dense black hole, its rotational speed dramatically increases, similar to the ice skater pulling in her arms. This spin creates a distorted space-time around the black hole, a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. The stability afforded by angular momentum conservation is fundamental to the long-term existence of planetary systems. A stable spin provides a consistent environment for life, as it dictates the length of day and night cycles and influences atmospheric circulation. Without this inherent stability, our planet's rotation might have slowed down erratically or even ceased, leading to vastly different, perhaps uninhabitable conditions. The fact that Earth has maintained a relatively consistent rotation for billions of years is a testament to the powerful and enduring nature of this physical law in the vacuum of space. In essence, the conservation of angular momentum ensures that once something in space starts spinning, it is incredibly difficult to stop it, or even significantly alter its rate of rotation without a substantial external force. Since such forces are rarely encountered in the cosmic void, The rotational motion of celestial bodies persists for unfathomable durations. This principle, alongside inertia and gravity, forms a triad of physical laws that govern the tireless movements of the cosmos. It paints a picture of a universe that is perpetually in motion, not because it is constantly being pushed or powered, but because the fundamental laws of physics, in the absence of significant opposing forces, dictate that things simply continue to do what they are already doing, whether that is moving in a straight line, orbiting a gravitational center, or majestically spinning on an axis. The universe is a grand, intricate mechanism. Once wound up, it continues to run, its celestial gears turning with an eternal, unwavering consistency, sustained by the profound elegance of physics. While the principles of inertia, gravity, and angular momentum elegantly explain the enduring motion of individual celestial bodies, the universe is rarely composed of isolated objects. Instead, it is a vast, interconnected tapestry of interacting systems. Moons orbit planets, planets orbit stars, stars congregate in galaxies, and galaxies cluster together. This intricate interplay means that the movement of any single celestial body is often influenced by the gravitational pull of multiple other bodies. It is a grand, continuous gravitational ballet where each dancer subtly, and sometimes not so subtly, affects the movements of all the others, ensuring the cosmic dance continues for billions of years, constantly being reshaped and re-choreographed by these complex interactions. Consider, for example, our own solar system. While Earth's orbit is primarily dominated by the Sun's immense gravity, it is not immune to the gravitational whispers of its planetary neighbors. Jupiter, with its colossal mass, exerts a noticeable, albeit small, gravitational tug on all other planets. Over vast timescales, these tiny nudges can subtly alter orbital eccentricities, inclinations, and even the rates of precession. These aren't strong enough to pull Earth out of its orbit, but they contribute to the long-term, cyclical variations in Earth's orbital parameters, known as Milankovitch cycles, which are believed to play a role in long-term climate changes and ice ages. The entire solar system is a delicately balanced gravitational machine, where the motion of each planet is a product of its interaction with the Sun and all its sibling planets. The stability of these multi-body systems is often a wonder to behold. Despite countless gravitational interactions over billions of years, the major planets of our solar system have maintained remarkably stable orbits. This stability is a testament to the fundamental arrangement and masses of the system. However, gravitational interactions can also be a source of dramatic change, particularly in more chaotic systems. For instance, the highly elliptical orbits of many comets are shaped by occasional close encounters with gas giant planets, whose strong gravity can perturb them dramatically, sending them either hurtling into the inner solar system or ejecting them entirely into interstellar space. Similarly, the paths of asteroids in the asteroid belt are not perfectly uniform, but are influenced by Jupiter's gravity, leading to gaps in the belt where resonant orbits are unstable. The concept of a gravitational dance truly comes alive when observing binary or multiple star systems. Many stars in the universe are not solitary, like our Sun, but exist in pairs or even larger groupings, orbiting a common center of mass. In a binary star system, two stars might trace elegant, often elliptical, paths around each other, constantly exchanging gravitational energy. The strength of their mutual gravitational pull keeps them bound together for billions of years, even as they journey through the galaxy. The beauty of these systems lies in their codependent motion. Each star's path is entirely defined by the other's gravitational presence, leading to a perpetual pirouette in the cosmic void. These gravitational interactions are not always perfectly smooth. Over immense timescales, complex gravitational forces can lead to subtle shifts in orbits. For example, the precise alignment of multiple planets can create gravitational resonances where the periodic tugs reinforce each other, leading to more significant orbital changes. Such resonances can sometimes destabilize systems, but often they can also lead to remarkable stability, locking orbits into predictable ratios like the resonant orbits of Jupiter's Galilean moons. Io, Europa, and Ganymede, for instance, are in a 1.2.4 orbital resonance, where for every orbit Io completes, Europa completes half an orbit, and Ganymede completes a quarter. This intricate, stable configuration is a direct result of their long-term gravitational interactions. On a galactic scale, gravitational interactions become even more profound and dramatic. Galaxies are not just collections of stars, they are immense gravitational entities that can interact with each other. When two galaxies approach, their mutual gravity can distort their shapes, drawing out long tidal tails of stars and gas. Over hundreds of millions or billions of years, these interactions can lead to spectacular galactic mergers, where two galaxies slowly coalesce into a larger one. During such mergers, stars rarely collide directly due to the vast distances between them, but their gravitational paths are completely reshuffled, creating new galactic structures. Our own Milky Way is currently on a collision course with the Andromeda Galaxy, a cosmic event that will unfold over the next few billion years, culminating in a merger that will transform both galaxies into a new elliptical giant. This is perhaps the ultimate example of a gravitational ballet, where entire star systems are reshaped by the mutual pull of colossal masses. Even within a single galaxy, the distribution of dark matter plays a crucial, though invisible, role on gravitational interactions. Dark matter, which doesn't interact with light but does exert gravity, forms a massive halo around galaxies. This gravitational presence influences the rotational curves of galaxies, preventing stars from flying off into space as they orbit at high speeds. Without the unseen gravitational embrace of dark matter, the beautiful, stable rotation of spiral galaxies would simply not be possible. Its gravitational interaction with visible matter is a key factor in ensuring the enduring motion of billions of stars within a galaxy. Furthermore, the continuous movement of celestial bodies allows for the crucial recycling of matter and energy throughout the universe. Stars, in their long lives, fuse lighter elements into heavier ones. When massive stars reach the end of their lives, they explode as supernovae, scattering these newly forged elements back into space. These elements, propelled by the force of the explosion and then carried by galactic currents, become the building blocks for new stars, planets, and even life. The motion imparted by gravity and inertia ensures that these elements are dispersed, collected, and reformed over and over again, preventing the universe from becoming a static, unchanging place. This constant motion is fundamental to the cosmic cycle of creation and renewal. Without this intricate gravitational ballet, the universe would be a far less interesting place. Planets would not form, or if they did, They would not remain in stable orbits around stars. Stars would not coalesce into galaxies, and galaxies would not interact. The dynamic, evolving universe we observe, filled with swirling nebulae, orbiting planets, and merging galaxies, is a direct consequence of the continuous, complex interplay of gravitational forces. These forces, acting in concert with inertia and angular momentum, ensure that everything is constantly in motion, ceaselessly shifting and reshaping, but always within the bounds of predictable physical laws. The subtle gravitational pulls from distant objects, once thought to be mere perturbations, are now understood as integral parts of the cosmic symphony. They add richness and complexity to the otherwise simple two-body problem, creating the fascinating, long-term evolution of systems like our solar system. These interactions can lead to both astonishing stability and dramatic, transformative events, such as the capture of smaller moons by larger planets, or the ejection of rogue planets into interstellar space. Yet, even in these instances of apparent chaos, the underlying principles of gravity and momentum conservation are always at play, guiding the narrative of cosmic motion. The enduring nature of these interactions means that the universe is a living, breathing entity, constantly adjusting and rebalancing itself under the influence of gravity. The movements we observe today are not merely a snapshot of a single moment, but the continuation of a dance that began billions of years ago and will continue for billions more. Each orbital period, each stellar rotation, each galactic drift is a testament to the patient, persistent work of gravity, weaving together the destinies of countless celestial bodies into a single, majestic, and unending cosmic ballet. It is a reminder that in the universe, nothing truly moves in isolation. Everything is connected by the invisible threads of gravitational force, forever influencing and being influenced in a dance that knows no end. Having explored the principles that sustain cosmic motion, a fundamental question remains. How did all this movement begin in the first place? If celestial bodies simply continue to move due to inertia, gravity, and angular momentum, what was the initial impetus, the spark that ignited the grand, eternal dance of the universe? The answer lies in the violent, chaotic, yet ultimately creative processes of cosmic formation, where raw materials from the early universe were forged into spinning, orbiting worlds, imparting the very first moments of motion that would endure for billions of years. This is the story of how from scattered dust and gas, the seeds of perpetual movement were sown. The vast majority of the celestial objects we observe today, from stars to planets and even galaxies, originate from the collapse of immense clouds of gas and dust. These primordial clouds, often called nebulae, are not perfectly uniform or still. Even in their diffuse state, they possess slight irregularities in density and minuscule inherent amounts of turbulence or slow rotation. This seemingly insignificant initial movement is the crucial starting point for everything that follows. The journey begins when a region within such a nebula becomes slightly denser than its surroundings, or when an external disturbance, such as the shock wave from a nearby supernova, compresses a part of the cloud. Under its own weak collective gravity, this denser region begins to contract. As billions upon billions of individual atoms and molecules are drawn closer together, the gravitational pull on them intensifies. This inward collapse is the very first form of motion in the birth of a celestial body, a slow, inexorable fall towards a common center. As the cloud collapses, Two key physical principles, which we discussed earlier, immediately come into play and become amplified: inertia and the conservation of angular momentum. Imagine the initial, vast cloud as an extremely slow, imperceptibly rotating entity. As its immense mass begins to contract and concentrate towards its center, its moment of inertia dramatically decreases. To conserve angular momentum, the cloud must therefore spin faster and faster. This is precisely what happens. The slowly contracting cloud starts to rotate more rapidly, just like an ice skater pulling in her arms. This increasing rotation is not a new force, but an intensification of an existing, albeit minuscule, initial spin. This is how the rotational motion, the axial spin of future stars and planets, is first imparted and cemented into their very being. Simultaneously, as the cloud collapses and spins, it doesn't just form a dense sphere. The rotational motion causes the material to flatten into a disk, much like dough spinning on a pizza maker's hand. This is known as a protoplanetary disk, if it's forming a star and planets, or an accretion disk, if it's around a black hole. Within this rapidly rotating disk, gravity continues its work. Particles of dust and gas, now moving in orbits around the central growing mass, begin to collide and stick together. These collisions, initially gentle, gradually lead to the formation of larger and larger clumps, a process called accretion. These accumulating clumps, often referred to as planetesimals, also possess kinetic energy from their orbital motion within the disk. As they grow, their gravitational pull increases, allowing them to attract even more material. The planetesimals sweep up debris in their orbital paths, clearing out regions of the disk. This orbital motion, a perpetual state of falling and missing the central star, is therefore inherent to their formation. The initial sideways velocity that keeps them in orbit is a direct consequence of the rotational motion of the entire protoplanetary disk itself, which in turn came from the initial spin-up of the collapsing nebula. Each piece of matter in the disk has a certain orbital speed and direction, and as they coalesce, they combine these individual momenta into the larger orbital momentum of the forming planet. Consider the formation of our Sun and the planets. The solar nebula, a vast cloud of gas and dust, collapsed, flattened into a disk, and began to spin. The central part condensed to form the Sun. Within the disk, dust grains collided and aggregated, forming pebbles, then rocks, then planetesimals, and finally the planets we know today. Each step of this process involved the transfer and conservation of angular momentum and kinetic energy. The planets inherited their orbital motion from the collective motion of the material in the protoplanetary disk, and they inherited their axial spin from the localized accretion and rotational dynamics within their growing masses. The forces at play during this formation are immensely powerful. The gravitational collapse releases enormous amounts of potential energy, converting it into heat and kinetic energy. The material falling inwards accelerates, building up tremendous speeds. While much of this energy is eventually radiated away as heat, a significant portion is locked into the orbital and rotational motion of the newly formed celestial bodies. This initial kick, this fundamental imparting of motion during formation, is what sets the stage for billions of years of continued movement. Even the formation of galaxies follows a similar pattern. Gigantic clouds of gas and dark matter in the early universe, possessing small initial rotations, collapsed under gravity. As they contracted, they spun up, flattening into the disk shapes characteristic of spiral galaxies, or the more chaotic ellipsoids of elliptical galaxies. The stars within these galaxies then formed from smaller collapsing clouds, inheriting the overall galactic rotation and adding their own localized orbital and rotational motions. The entire galactic structure, with its hundreds of billions of stars, gas, and dust, is a colossal system built upon the conservation of angular momentum from its earliest moments. It is crucial to understand that these initial motions are not just random. They are an intrinsic consequence of the gravitational collapse and the conservation laws of physics. The universe doesn't have an external motor that continuously winds up its celestial clockwork. Instead, the motion is wound up at the very beginning, during the violent but structured processes of formation. Once that initial motion is imparted, the absence of significant opposing forces in the vacuum of space, combined with the continuous guiding hand of gravity, ensures its persistence. Therefore, the enduring movement of celestial bodies for millions of years without stopping is not a mystery, but a testament to the efficient and self-sustaining nature of the universe's physical laws. The energy for this perpetual motion was effectively paid for up front, converted from gravitational potential energy into kinetic and rotational energy during the birth of stars, planets, and galaxies. Once transformed, this energy of motion remains largely conserved because there are no effective mechanisms in space to dissipate it over cosmic timescales. So, when we look at the night sky and observe the serene, unchanging paths of planets and the steady glow of distant stars, we are not witnessing static objects. We are seeing the echoes of creation, the direct result of the universe's formative moments. Each spin, each orbit, is a living relic of the chaos and order that brought these bodies into existence, a continuous reminder of the initial impulse that set the cosmic ballet in motion billions of years ago. The universe is a masterpiece of dynamic equilibrium, where the very act of formation ensures the longevity of motion, allowing worlds to turn and stars to burn for countless eons, all without ever running out of fuel for their fundamental movements. Having journeyed through the foundational principles of inertia, gravity, angular momentum, and the initial imparting of motion, we arrive at the profound conclusion: the enduring dance of celestial bodies is not merely a phenomenon, but a fundamental characteristic woven into the very fabric of the cosmos. Their perpetual movement for billions of years without stopping is a testament to the elegant interplay of physical laws and the vast emptiness of space, painting a picture of cosmic longevity where motion, once initiated, persists almost eternally. This is the story of the universe's grand waltz, a silent, majestic performance that continues to unfold over timescales that humble human imagination. The lifespan of a celestial body's motion is almost unfathomable from a human perspective. Our Sun, for example, has been orbiting the center of the Milky Way for approximately 4.5 billion years, and will continue to do so for billions more. The Earth has spun on its axis and circled the Sun for an equal duration, maintaining the rhythm of day and night without fail. These are not ephemeral events. They are persistent, fundamental processes that define the very existence of these bodies. The sheer duration of this motion underscores the near-perfect efficiency with which the laws of physics operate in the cosmic environment. There are no significant forces working to bring the system to a grinding halt, allowing the initial kinetic and angular momentum to be conserved for eons. This cosmic longevity has profound implications for the evolution of life and the universe itself. The stable, long-lasting orbits of planets around stars, maintained by gravity and inertia, provide the consistent conditions necessary for the emergence and sustained evolution of complex life forms. If planetary orbits were prone to rapid decay or sudden changes, the window for life to develop and thrive would be drastically reduced. The reliable succession of seasons, the consistent amount of solar radiation, and the very existence of a stable liquid water environment are all direct consequences of the enduring orbital motion of Earth. Without this millennia-long stability, the intricate biological processes that underpin life as we know it would simply not have the time to unfold. Furthermore, the continuous movement of stars within galaxies and galaxies within clusters ensures the dynamic evolution of the universe on a grand scale. The constant motion of stars, driven by galactic gravity, leads to occasional close encounters, which can influence planetary systems or even trigger stellar collapses that create new elements. The gravitational interactions between galaxies, leading to mergers, redistribute stars, gas, and dark matter, fueling new bursts of star formation and creating larger, more massive galactic structures. This ongoing motion is not just about individual objects, it is about the constant, large-scale reshaping and renewal of the entire cosmic tapestry. The universe is not a static painting, but a vibrant, ever-evolving sculpture, constantly being molded by the relentless, enduring movements of its constituents. The near-perfect vacuum of space is the silent stage upon which this eternal drama unfolds. Without the drag of an atmosphere or the friction of solid ground, the mechanisms for dissipating kinetic and angular momentum are almost entirely absent. This fundamental characteristic of the cosmos, its vast, empty spaces, is as crucial to the longevity of motion as the forces that initiate and guide it. It is an environment designed for persistence, where once a billiard ball is struck, it rolls forever. Or rather, where once a star begins to spin, it spins for its entire stellar lifetime. This cosmic emptiness allows the universe to run its course for billions of years without needing a constant external push, preserving the energy of motion imparted at its birth. Even the subtle changes that do occur, such as the gradual slowing of Earth's rotation due to tidal interactions with the Moon, are not indicative of an eventual cessation of motion, but rather a redistribution of angular momentum within the system. These are not energy losses from the system, but rather internal adjustments that ensure the overall conservation of angular momentum is upheld. These slow, almost imperceptible shifts over geological timescales contribute to the dynamic, evolving nature of celestial systems without bringing them to a halt. They are part of the subtle, internal choreography of the gravitational ballet, adding layers of complexity and long-term evolution to the enduring dance. The elegance of these principles lies in their universality. The same laws that govern the spin of a planet also dictate the rotation of a galaxy, and the same gravitational attraction that binds a moon to a planet also orchestrates the orbits of entire star systems around a galactic center. This universal applicability means that the understanding we gain from observing our own solar system can be extended to the most distant reaches of the observable universe, allowing us to predict and comprehend the long-term movements of objects that are billions of light-years away. It speaks to a cosmos that is fundamentally orderly, governed by a set of consistent and enduring rules that apply everywhere and at all times. The sheer scale of cosmic time and distance is also a factor in perceiving this longevity. When we say celestial bodies move for millions of years, we are speaking of periods far beyond human experience. Our entire recorded history is but a blink in the eye of cosmic time. Yet, for stars and planets, millions of years are just a fleeting moment in their billions of years-long journeys. It is this vastness of scale, combined with the efficient conservation of momentum and energy, that allows for such astonishing persistence of motion. The universe is patient, and its inhabitants, once set in motion, embody that patience through their endless journeys. Ultimately, the reason celestial bodies move for millions of years without stopping is not due to some mysterious, continuous energy source, but rather the elegant combination of fundamental physical laws and the nature of the cosmic environment. Inertia ensures that things keep moving unless stopped. Gravity continuously bends these straight paths into stable orbits. Angular momentum ensures that rotational motion persists, and the vast, almost perfect vacuum of space ensures that there are no significant opposing forces to dissipate this motion over cosmic time scales. The initial energy imparted during the birth of these bodies is simply conserved, allowing them to carry out their grand, silent, and endless dance. This realization transforms our understanding of the universe. It is not a place where objects are constantly being pushed and pulled by active engines, but a system that, once set in motion, sustains itself through the inherent properties of matter and space. It is a universe where motion is the default state and stillness is the exception, always requiring an external force to achieve. Every glittering star, every orbiting planet, every swirling galaxy is a profound testament to this cosmic truth. The universe is alive with eternal motion, a continuous, majestic ballet that began billions of years ago and will continue for billions more. A timeless story written in the movements of celestial giants and the quiet persistence of universal laws. So, as you drift towards sleep, let your thoughts settle on this enduring cosmic rhythm. Imagine the earth beneath you, silently spinning, eternally circling the sun. Let the vastness of space and the patience of cosmic motion cradle your mind. It is a beautiful, self-sustaining system, and we are privileged to witness a tiny fraction of its unending performance.